Alrighty! Good morning, everybody. Welcome back to non-Euclidean geometry. Plan for today, we're going to talk about PPP attempts, which stands for parallel postulate proof attempts. And look through history about how several different mathematicians attempted to prove Euclid's parallel postulate. I've got my usual office hours today and Wednesday after class and at 2. Tomorrow at 11 and at 1. And as far as homework goes, you all have a homework due today. Make sure I have that before you leave. And also, I'm going to do a quiz this week on quadrilaterals. But I thought I would mix things up a little bit, and since I don't particularly care if we do that quiz on Wednesday or Friday, I thought I'd put it to a vote to see when you all wanted a quadrilaterals quiz. Your options are this Wednesday or this Friday. Who would prefer to do one this Wednesday? 1, 2, 3, 4, 5, 7. How about this Friday? 1, 2, 3, 4, 5, 6. Okay. By a margin of 1 vote, the Wednesdays have it. Oh, shoot. I should have voted for Friday, admittedly. Now I have to make one and then write a quiz the next day. Okay, so on Wednesday we'll have a quiz on the quadrilaterals. Just pass back the last quiz. I know I'm a little bit behind in posting solutions and such to things on Canvas. My apologies. I'll try to rectify that mistake a day or two tomorrow. Yeah, does anybody have any questions or comments before we get started for today? Why do atheists have so much trouble dealing with exponents? Dave?
They believe in higher powers.
Because they don't believe in higher powers. So, today we're going to take a little bit of a break from looking at what things can we prove in neutral geometry and what properties can we say that triangles and quadrilaterals, etc., all have to have in a Hilbert plane. And we're going to move from chapter 4 in the book. Oh, I have a packet. I should probably pass that out on top. We're going to move from chapter 4 in the book to chapter 5 in the book. And go to talking about the history of the parallel postulate and how various mathematicians throughout the ages have attempted to prove it. Because as we kind of mentioned in the very first packet of the semester, parallel postulate, a wee bit controversial. So Euclid himself included it as an axiom, but mathematicians thought, I don't like this. This feels more like something we should be able to prove than something that we should just assume as an axiom or a postulate. And so I'm going to talk a little bit about how a few different mathematicians attempted to prove it and came up with some interesting mathematical results along the way. So to start with, we're going to go with good old Proclus, who was a Greek philosopher, also called Proclus the Successor, Proclus the Platonic Successor, or Proclus of Athens. He was a very influential Greek Neoplatonist philosopher. Okay, look, he's a Greek guy who lived in kind of who was born around 465-ish AD, following in the tradition of Euclid. Thought, I wonder if we could improve upon the elements by actually seeing if we could prove the parallel postulate, and so from there on out include that as a proposition rather than as its own separate axiom to assume in proving everything else that Euclid does in Euclidean geometry. So let's take a look at Proclus's proof. of the parallel postulate. So here's the scoop. We're going to be trying to prove kind of the more modern version of the parallel postulate, which says that if you have a line L and a point P, I need to give myself more room to do this. So this is our line L and this is our point P. We want there to exist a unique point that or a unique line that passes through P and is parallel to L. So we're going to assume that we have a line M that we already know passes through P and is parallel to L. We're going to assume that there's a second line that passes through P, and we're going to try and show that that other line that happens to pass through P cannot possibly be parallel to L. So here's our, so I say our, I shouldn't claim credit for someone else's work. Here is what Proclus did as part of his proof. So he said that given two parallel lines, M and L, we're going to suppose that we have another line N which happens to intersect a line M at a point P, and our goal is to then show that N has to intersect L. So we're supposing we have some other line N that happens to intersect M at the same point P, and what we're going to show is that N cannot possibly be parallel to L. Because if we can show that, then that would show prove the more modern version of Euclid's parallel postulate. That given a line L and a point P, we can't have multiple lines passing through P that are both parallel to L. And I guess and one thing I should start with is it was already known at the time of Proclus that there's at least one line M that passes through P and is parallel to L. What was unclear at that point is, could there be more than one line that'll pass through P and be parallel to L? And so Proclus says, no, that ain't happening. So first thing we're going to do is we're going to let Q be the foot of the perpendicular from the point P to the line L. In other words, pick a point. We're going to find a point Q on L, such that if we draw the line from P to Q, we get a right. And this is something that at the time of Proclus it was known that we could do in Euclidean geometry, is given two lines and a point on one line, given two parallel lines, M and L, and a point P on M, we can find a point Q on L that'll make this segment perpendicular to both M and L. And now, already breaking the new chalk. So now, we're going to assume that PQ is not a part of the line N, because if PQ happens, if this segment happened to be part of the line N, then clearly N is going to intersect L at the point Q. So we can assume that the segment that N is not equal to the line between P and Q, as otherwise N clearly has to intersect L. At the point Q. If N and the line between P and Q were the same line, then obviously N can't possibly be parallel to L. So then, what does that mean? Well, if we notice then, that's going to imply that we are going to have a ray of N, namely, let's say this ray right here, from P to some point Y, that's going to be in between PQ and this other ray up here, P going to the right on M, assuming that N and PQ are not the same line. So then, one ray, which we'll call PY, of N, is going to lie between the ray PQ and a ray PX of the line M, or just for fun, X, we're going to assume is the foot of the perpendicular from Y to M. So if we draw this, go up here to intersect at a right angle at M, we know that either this ray, that if N is not equal to PQ, then a ray of N has to be in between PQ and some PX like this. It also could be on the left side of PQ, but if it's on the left side, then you just flip your drawing over so it's on the right side instead. And now, here comes the crux of Proclus's argument. Proclus is basically going to say, let's take this point Y and kind of move it back and forth on our line N. And specifically, let's move Y so far down the ray so that eventually we're going to end up with a point Y down here where the distance from X to Y is greater than the distance from P to Q. So in other words, we can say that now, as we move the point Y further and further from the point P on N, xy must increase without bound. Meaning there's no upper bound on how far away x and y will get from each other as we move y further and further to the right along this line here along N. And so eventually, we're going to end up in the scenario where xy has to have a greater length than PQ. Our original point P and the perpendicular and the foot of the perpendicular to L here, Q, that are kind of these fixed points on M and L. So in other words, we take this point Y and we slide it along until eventually X and Y are further away from each other than P and Q are. And then at this point, Y must be on the other side of L. Hence, between this position and its starting position, if Y originally was on the top side of L and ended up down here on the bottom side of L, there had to have been a point in time where Y had to have been on the point L. If it goes from being on one side of L to being on the other side of L, there had to have been a point in time where it had to be on L exactly. The starting, hence between the starting position and this position and starting position, Y must have been on L. Thus, N intersects L. So the Euclidean parallel postulate, which I'm going to label as the EPP the F must hold. Notice here I'm saying the Euclidean parallel postulate rather than something like Hilbert's Euclidean axiom of parallelism, because A, rolls a little bit nicer off the tongue, and B, Hilbert, Proclus is doing this around the year 500 or so. Hilbert didn't come around for another 1,400 years. And so the idea of having a Hilbert plane or Hilbert's Euclidean axiom of parallelism, that was not a thing yet. So the crux of the argument is you can't have multiple lines passing through P that are parallel to L, because if N is one such line and N is some other line that intersected P, by this sort of construction, you should be able to show that there exists that N has to intersect L, either at this point here Q or at some point Y along this ray that we get here. Here's my job for you all. Why didn't this proof just once and for all settle the debate about why the Euclidean parallel postulate can't just be proved in Euclidean geometry? So why don't you all take a few minutes, talk with your neighbors, and see, do you have any issues with this proof? Is there anything that was assumed that we shouldn't really have maybe assumed? Is there any result here that relies on circular logic? Is there anything fishy that you can find with this proof? Let's go take a few minutes, and then we'll come back together as a class and then discuss what y'all think of this so-called proof of the parallel postulate. What's that mean?
I said, I think this is what
Like, there's something fishy here. Gosh, Proclus might as well be in negative proof right here.
Exactly, literally. It's great if you've seen something like that, I'm like, this too. Especially in this class, it seems where you're like, I don't know what rules we're under. Yeah.
Well, I will say this, that depending on what rules we're allowed to use, there's nothing wrong with this proof. The proof kind of isn't a matter of like, that's not going to happen in Euclidean geometry. The issue is more along the lines of,
I'm kind of assuming that
Yeah, I was just saying, that
yeah, the part that I like the least is, at this point, y must be on the other side of L. Nobody said that they have to do the same, they're parallel lines, but nobody said that they have to do the same. Like, it's obvious, but nobody said that.
I meant to say this. Comment to the class real quick. Something else you might look for is there anything in this proof that relies on having intuition from the picture rather than something that occurs just from logically following from things? What's that? I'm not just trying to lead you up on a long case.
That'd be awesome.
Well, to start with,
I've done that before. I'm not doing that.
Well, I mean, I kind
Right, but it
Yeah,
didn't
but why
develop.
go on forever
Okay.
and eventually hit it
Okay, did you see it? I just think it's like the one that
and then
really
link is gonna like intersect which you can't show in a picture. You're gonna have to assume it's gonna go down.
So we're trying to prove that the Euclidean parallel postulate.
Yeah, no, both of them are sketchy.
You're assuming that it's going
Yeah,
to.
you're right. But you see that which is already secretly assuming basically
One way,
that,
It's true for my fact that it intersects.
and he doesn't have justification for that one line either.
I don't want to say that it's for the reason necessarily, but it seems
I mean,
like
you're
we're
just-
saying.
What's that? So what's the
That's
date?
what you want to live, yeah. I keep writing it that way because if I forget, it'll be embarrassing when I get back to
Right.
it. I don't know how
It's
to write
not
it.
parallel because it's
That's like a model. No, we couldn't.
It always.
He's saying it's
1000.
it's always something. Could we do that in show?
You know, November has been crazy. It's so many ones. November 11th, I was like.
We could show that.
It would be so close to
Move
being
something
M,
and see that.
and then you rotate it like.
And then you're drawing the perpendiculars from here to there. And that's
I don't know if I like
then you're showing this.
We're assuming Euclidean geometry where we don't assume, where we assume the first four postulates but not the parallel postulate.
Hilbert, he hardly exists.
Well, is it?
Hilbert, he ain't been born yet.
Good one, Dr.
But the thing is that.
Wow. Maybe he was. David Hilbert transcends time.
Oh,
Isn't that suggestive?
yeah.
Well,
He is a higher. He is a higher power. I mean,
David Hilbert is an excellent, just like David Gabler.
let's take 2 to the power of David Hilbert equals
I think.
David Gabler.
Yeah.
Solve for David Hilbert.
I actually don't solve for David.
The log.
Log base 2 of David.
Wait, the lock?
I know where I'm going with this.
The log base 2 of David.
Tell me that I'm wrong.
Oh, dang, she's
What does that mean though?
I don't know what that is. I'm gonna erase this now.
No. If you write that up on the board, you gotta put like a little hat over David Hilbert. He's always wearing a hat.
Because what?
He's always wearing a hat.
Hilbert's always wearing a hat.
This is
There
true.
you go.
Did they even have hats invented when he was born?
It wasn't. Nice.
Wait.
Put a hat on. I think they got the
Oh, he gave us a Christmas hat.
I love Christmas.
That was where I was.
I thought it was a propeller hat.
I like that better.
No, the Christmas
No, that's
hat.
what you would be wearing.
Yeah, no, that's what you're wearing.
Gabler's got the Christmas hat.
Yeah.
What a propeller hat, kind of.
That just
What?
actually looks more like
That's
a.
more Christmas.
See?
This is star on top of the tree.
All right, you've all had enough time to think about this.
Why can't this just be like, why are you stupid?
What do I want to erase? I don't want to erase anything.
Wait, what's pH? Oh, it looks like it's.
All right, let's come back together. Does anybody have any parts of this proof that they took issue with? Jack?
I am not sure about the xy must increase without bound, because
That is y moves along. That is y gets further and further from p. X y has to get further and has to get arbitrarily along.
right, because that's kind of assuming that n is getting further and further away from m, but there's no sort of reason to believe that other than like we drew it that way, and I don't know what the proof would be for as y gets further down along the ray, xy gets bigger.
Let's see. We have an acute angle, and we're saying that as we take these line segments that get further and further down the angle, they get longer and longer and arbitrarily long. Feels like something we've talked about recently. Sounds like a particular axiom that we may have seen on Friday. Yeah, Jack?
So that one's Aristotle's angle unboundedness axiom.
Yeah, actually, I think, Jack, that would come as a direct result of having Aristotle's angle unboundedness axiom. That, which is the one that said if you have an acute angle and basically lines going from one to the other ray perpendicularly, no matter how big a segment you start with, you can always get points that are far enough out along these two rays that the distance between them is, or that the segment you get between them is greater than any other segment that you could possibly start with. But that's reasoning.
Oh. No, you go first.
Don't tell me what to do. You go first.
I was about to move on to another angle of attack, so you can talk about this one first.
Okay, yeah, I want to talk a little bit more about this one first. Raises an interesting question, though. Nowhere in the Elements did Euclid have Aristotle's angle unboundedness axiom. So I'd say this is my first issue. Is we're assuming. By the way, if you go to the next page in the packet, I give you a place to write what issues are there with Locus proof. We're assuming Aristotle's axiom to say eventually that we can make xy be greater than pq. If we assume Aristotle's axiom, then I would say that that's something that's perfectly fine to say that we could eventually write that out. But we're assuming that. Kate.
So, when we introduced Aristotle's axiom, we were saying that it comes from assuming parallel postulate. So, like,
If we're working in that any Euclidean plane, Aristotle's axiom has to hold true.
yeah, but it's like in this picture, he's assuming that x and y are getting further apart because he drew n already not parallel to L. So it's like he's already assuming they're not.
Yeah, there's already kind of an assumption here that we're not getting another parallel line going on here. And I think the issue you mentioned, Kate, actually comes from, I would say, this part of the proof right here. That there exists a ray of n that lies between PQ and PX. Turns out that's actually okay, due to some stuff in Euclidean geometry that we didn't talk about. You can, this part of the proof is actually okay to say that there's a ray, Py, going between PQ and P, and I don't know, this ray up here. That is something we can prove in Euclidean geometry without the parallel postulate. But it is a good observation that it is something that we didn't really dwell on. Like, how do we know that there has to be a ray that does this, so to speak? Jared, you had something you wanted to say?
Yes. We over here, Luke came up with it, was we're thinking that the biggest problem is he assumes a notion of distance. In other words, he thinks that parallel lines are always the same distance away from each other, and you can see that in the diagram. But it's possible that L is also getting far away from M.
Ooh, that we have sort of this fixed distance that we would call perpendicular distance from P to Q.
Yes.
And you're saying, well, what if we have lines that sort of do this sort of thing?
And in the Poincaré disk, which I know is not probably doesn't follow some of the other Euclid postulates, you actually can get something where you have two parallel lines, because you got a lot of parallel lines, and the perpendicular crosses at some point and then stops crossing.
Actually, Jared, spoilers for like 2 pages in the packet from now.
Oh, cool.
But yeah, I would say that's an issue, is that we're assuming there's some fixed distance between the two lines, at least a fixed perpendicular distance, where you draw perpendicular lines from one to the other. Because obviously I could say, oh, well, I could have a bigger distance by doing that, but that's not a perpendicular distance. Does it make sense? I'm doing a bad job of describing what I mean by perpendicular distance. That if we had 2 pairs of lines, P to Q here, and then P prime to Q prime here, both of which form right angles between M and L, then they have to be the same fixed distance. Yeah, I would say that's definitely an issue. Assuming a fixed distance between parallel lines drawn perpendicularly. And on the next page, we have a more precise term for this. Need it?
My hand wasn't really up, but I was wondering, can you just kind of assume that the lines are parallel, that M and L are parallel?
We're assuming that we have that to start with.
Okay.
I think that's okay. Like, we're assuming that M is one line through P that's parallel to L. We're showing there can't be another. And it was known at the time of Proclus, independent of the parallel postulate, that there did have to be at least one line through a point P that is parallel to L. Okay?
Is there a problem where it's saying that because xy is less than pq at one point in time, and xy is greater than pq at one point in time, that n has to intersect L? Like, there's that sort of a continuity assumption being made there?
That assumption that if xy is less than pq here and xy is greater than pq here, that means that there had to have been a point in time where y went from one side to the other and thus has to be lying on L exactly. I think that's a big issue. How do we know that there had to have been a point in time where that point y was exactly on L if it went from being xy less than L to xy greater than L? In other words, this part of the proof. Why does that follow? I think that's something I took great issue with. If xy goes from, I'm just going to say less than pq to greater than pq, why does that imply y must have been on q at some point in between? And that's something I would say that certainly feels intuitively obvious from looking at the picture. Oh, if we're taking this thing and it's smaller here and it's bigger here, then clearly at some point they must have been matching up exactly. And then that also gets into what Jared mentioned, like, oh, we have this fixed perpendicular distance from one line to the other. Clearly, if pq equals xy and right angles, blah, 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 then y must have been on L at that point in time. Yeah. That's something that maybe feels intuitively obvious from looking at the picture, but there's not really any logical explanation for why does that have to happen. Any other comments from looking at Proclus's proof? Yeah, I would say kind of those are my main issues when I was looking at this sort of underlying assumption of Aristotle's axiom to say that xy can get arbitrarily long by just picking a point y that gets further and further from P. And also the assumption that just because xy goes from being less than pq to greater than pq, that means at some point y had to have been on the line L. It feels intuitively obvious, but doesn't really have like any logical explanation to back it up. So, yeah, mathematicians at the time of Proclus were like, yeah, maybe this is a little bit fishy. And so, work on the parallel postulate continued. So, something else, a guy with a really cool name by the name of, I don't know how to actually pronounce this, but I'm going to guess it's something like Posidonius. It's like Poseidon, but with a Donius at the end. And about the year 150 BC, said, all right, let's mix things up a bit and redefine what it means for two lines to be parallel. And see if we come up with another definition for parallel lines. Can we necessarily say that, can we make the Euclidean parallel postulate follow a little bit easier than just from saying two lines are parallel if they don't have any points at which they intersect? So you propose to say that two lines are parallel. If all the perpendicular segments dropped from one to the other are congruent. So Jared, this is kind of getting into something that you were remarking on earlier, that like, is that something that necessarily follows? Which basically the idea here is if we have a line M and we have a line L, and we're not a priori assuming any pre-existing relationship between M and L, like we're not assuming, for instance, that they don't have any points in common. What Postulate says is that if we take any two points, let's say on M, drop a perpendicular line down from P to L, let's say at this point Q, this is our point Q prime, and heck, let's do another one with hats, because you all seem to like hats. If any time that we drop a line from M down to L in a way that intersects L perpendicularly, if these segments are all congruent, that is how Postulate proposes that we say we can use as a definition for two lines being parallel. Not the two lines never intersect, but instead these perpendicular lines that we drop down here are always going to be the same, no matter what point on M we started with, or for that matter, if we started with a point on L and went up this way. What do you all think about that definition? Yes, Jared?
Is it a definition or a one-way conditional?
He chose to treat this as a definition.
Oh, well then I don't like the first half, the parallel implying that.
That parallel implies that the perpendicular lines we drop from one to the other have to be congruent?
Yes, the other half's fine.
What if I told you that in R2, this checks out?
I would believe you.
What would you say if I told you that you were under contractual agreement to pay me $100 by the end of today?
Show me the contract.
I was going to say, don't believe me just because I say something.
Oh, I mean, I think about it too.
Okay, good. Okay. Turns out I would argue that in R2, with the way we would draw out lines in a two-dimensional plane space, I would say that we could make this an if and only if statement, that two lines are parallel in the usual sense that they don't intersect, if and only if the perpendicular segments dropped from one to the other happen to be congruent to each other.
I move that you're assuming the Euclid's parallel axiom by using R2.
I assume I'm using Euclid's parallel postulate somehow here. Well, right now we're not assuming. Right now we're taking a break from trying to prove the parallel postulate.
Okay. Aha.
Sort of. So, here's my question for y'all. This is equivalent to our usual definition in R2. Is this equivalent to our usual definition of parallel in all the other models we've seen, like the Poincare disk and spherical geometry and U and Q2 and yeah, any of those? Brian, I see you shaking your head.
When we did U, we had many parallel lines for each of them, but the parallel line didn't necessarily have to have the same distance if you dropped a perpendicular line?
That's interesting. Would you like to draw a picture to
Sure.
show what you mean? Feel free to erase anything on this left-hand board.
She's got it.
Dad Zeus. So you're saying that. What are you sitting back down for?
Oh, okay.
Stand by your words. Both, just literally and metaphorically. So you're saying that so you're saying that it's possible to have two lines that don't intersect, that if we draw a perpendicular from one down to the other, we don't always necessarily get congruent segments?
Yes.
What do y'all think? Sounds like an issue to me. Yeah, nice job, Donna. Yeah, problem is, Jared, I think this is what you were saying earlier. While this may be equivalent to our usual definition of parallel lines in R2, it doesn't quite work in all of our other models. Like it doesn't work in U, it doesn't work in spherical geometry, it doesn't work over the Poincare disk. U is an interesting example because U actually has properties like 180-degree triangles and such, which are similar to which are things that Euclidean planes have. But even still, this is equivalent to our usual definition of parallel in R2. But not in other models. And yes, Jared, assuming that we're working in R2 does mean assuming we have the Euclidean parallel postulate. So as an approach, I would argue that trying to redefine parallel lines in a way that makes the Euclidean parallel postulate easier to prove, I would argue that's maybe not so good an idea. Because it's possible to have models of geometry in the usual way that we have of thinking about geometry, and certainly in the way that Posidonius was thinking about geometry. This is equivalent to the definition we're used to working with of two lines are parallel if they never intersect. But that doesn't mean that in every model of geometry that satisfies things like all right angles are congruent, etc., it's going to necessarily come out to be the case that this definition is logically equivalent to our definition of parallel as lines not intersecting.
So would we say that if you're trying to say that these are logically equivalent and you try to prove this version of it, then it would be relying on some kind of Euclidean intuition?
Yeah, it would be relying on some kind of Euclidean intuition or relying on some property that ends up being logically equivalent to the Euclidean parallel postulate, I would say. And in essence, you can't prove that this is equivalent to usual definition of parallel without somehow relying on the Euclidean parallel postulate in some way. Or at least just relying on visual intuition, which is not something we consider as a valid logical proof technique, so to speak. Any questions or comments about Posidonius' definition of parallel lines? In that case, here's a whopper of a definition for you. The equidistant locus to a line through a point, where given a line L and a segment PQ, of a line that's perpendicular to L at some point Q. So, I'll write this one down. Why not? Given a line L and segment PQ of a line perpendicular to L at a point Q, the equidistant locus. Why am I writing this all down? I don't have time for this. I'll see. Locus 2L through P is basically the set of all points that if the all points P prime on the same side of L as P, such that if Q prime is the foot of the perpendicular from P prime to L, then PQ is congruent to P prime Q prime. Let's draw a picture. That's what I should have started with. So here's the scoop. We got a line L. We got a segment PQ that's going to be perpendicular to L. And we can talk about the equidistant locus to our line through P as being the set of all other points that if we happen to look at those points, say P prime, and drop the perpendicular down to L, we get a segment of the same length. So P prime would be on this equidistant locus because the perpendicular from P prime down to L is congruent to the perpendicular from P down to L. Another point that would be in this equidistant locus would be a point P prime over here because these segments have the same length. Here's a third one, P double hat.
Skip the P hat, go right for the
What's that?
Skip the P hat, go right for the money.
Skip the P hat, go right for the money. So here's my question. What do all of the points that are on the equidistant locus to the line L through P have to have in common in this picture? Megan? They all have to be collinear, and they're all going to give us the line that they define is going to be a line that's parallel to L. So it's going to turn out to be the case that this line M, that we're going to get a line M that happens to be parallel to L by drawing out what is the equidistant locus to our line L through the point P, at least in R2. That if you pick a point P that does this, pick any point P, the points you're going to get are going to get the line. Now technically we could also say something like, let's say P hat's hanging out down south for the winter. And look, it has a segment that's of the same length. That's why in our definition that we're saying it's defined to be the set of all points on the same side of the line as our point P. Because otherwise our equidistant locus would technically be like two lines rather than just a single line. We want to eliminate the possibility of having a line like this by saying all of our points have to be on the same side as the point P. So in R2, this equidistant locus to L through P is going to define a line that's parallel to L. You think that's going to happen in some non-Euclidean models? We'll talk about this more on Wednesday. So on Wednesday, when we come back together, we're going to talk a little bit more about this idea of equidistant locus to a line through P and why this is just going to give us a nice parallel line M in R2. We'll compare that to what happens in some other models of geometry. Y'all have a good rest of your day. I will see y'all on Wednesday. Oh yeah, don't forget, you have a homework due today, and on Wednesday we'll have another quiz.